Welcome back to the deep dive. Today we're digging into something pretty fundamental, really the invisible backbone of our digital lives.
That's a good way to put it.
Yeah, I mean, every email you send, every video call, every file transfer,
Yeah.
it all relies on this basic assumption that your data just arrives perfectly, you hit send, and, you just expect it to be accurate.
It's a fundamental trust we place in the tech, isn't it? But the reality, the physics of transmitting data over any distance, is that it's actually far from perfect.
Right.
Imagine sending, say, a critical report or even just a text message, and somewhere along that path, just a tiny piece of information gets flipped. A 0 becomes a 1, or, vice versa.
Ooh, yeah. What happens then?
Well, the consequences could range, right? From maybe a minor glitch in a picture to, well, potentially critical errors in financial data or commands.
So our mission today, our deep dive, is really to unpack how computer networks, specifically what they call the data link layer, act as these silent guardians. We want to explore the essential techniques and protocols that prevent these errors, manage the traffic on shared channels. Basically, how devices can all talk without shouting over each other.
And how these foundational ideas shape something we all use, probably without thinking about it, Ethernet.
Exactly. It's about ensuring your bits arrive as you sent them and how devices, well, take turns talking.
It really is a testament to some ingenious engineering. I mean, without these protocols working behind the scenes, our connected world just wouldn't function reliably. It'd be a mess.
Okay, so let's start with the basic challenge. These errors. What actually causes a 0 line to flip to a 1? What's going on?
Well, primarily it's interference. Think of it like static or noise on any signal, but for digital data.
Okay.
During transmission, these electrical signals or even optical signals, they can get distorted, and that distortion can cause those bit flips.
Right.
We generally categorize these into two main types. First, there's a single bit error. That's where just one bit changes within a data unit, like a byte or maybe a whole packet.
Okay, 1 bit. Seems like maybe you could handle that. But you mentioned 2 types. What's the other?
The other is what we call a burst error. And this one's a bit trickier.
Okay.
A burst error means 2 or more bits have changed within that data unit. Now, the crucial thing here is that these corrupted bits don't actually have to be next to each other.
Ah.
The length of the burst error is measured from the first corrupted bit to the last corrupted bit, even if lots of bits in between are totally fine.
So it could span quite a bit of data, even if only a few bits are actually wrong within that span.
Exactly. And that distinction really matters because, well, a burst error is generally much harder to deal with than just a single flipped bit. It needs more robust error control.
And why is getting this right so absolutely critical?
Because for so many applications, think financial transactions, medical records, even just streaming video reliably, data integrity is non-negotiable. If errors aren't caught and ideally corrected, the data's reliability is compromised, sometimes with really severe consequences.
Okay, so it's a big deal. How do we fight back against these digital gremlins then? What's the fundamental solution?
The central concept, the core idea behind almost all error detection and correction is redundancy.
Redundancy, okay.
It's actually quite elegant when you think about it. To detect or correct errors, we simply send extra bits, redundant bits, along with the actual data we care about.
So padding it out somehow.
Sort of, but in a structured way. The sender adds these extra bits based on the data itself. The receiver then uses these redundant bits to check for errors, or in some cases to actually fix them.
Oh, okay.
And then once the checks are done, assuming everything's good or has been fixed, the receiver just strips away those redundant bits, leaving you with, hopefully, the original, pristine data.
It's kind of like sending a package with a special seal. Maybe one that not only shows tampering, but maybe even hints at where the tampering happened.
That's a pretty good analogy, yeah.
So this brings us to a really key distinction you mentioned. Error detection versus error correction. I'm guessing one is much harder.
Oh, absolutely. Error correction is significantly more difficult. For detection, all we need is a simple yes or no answer. Did an error occur somewhere in this chunk of data?
Okay, just flag it.
Right. But for correction, we need way more information. We need to know the exact number of bits that got corrupted and their precise location within the message.
Okay.
And figuring that out demands significantly more redundant bits than just simple detection requires.
So let's say we do detect an error. What are the options then? How do we fix it?
Well, there are two main paths networks typically take. The first is called forward error correction, or you'll often see it as FEC.
FEC. Okay.
Here, the receiver actually uses those redundant bits to try and guess or deduce the original message. It has enough built-in information to potentially fix the error right there on its own without needing to talk back to the sender.
Like a self-healing message. Pretty neat.
It is very clever, yeah.
Hmm.
The other main approach is retransmission. This is often implemented using protocols called automatic repeat request, or ARQ. In this case, if the receiver detects an error, it basically just throws up its hands and asks the sender, hey, can you please send that message again?
Okay, simpler in concept maybe, but involves more back and forth.
Exactly. It's a very common and highly effective method, especially in network protocols where you expect the channel to be reasonably reliable most of the time.
So these redundant bits,
Mm-hmm.
how are they actually generated and added? It's not just random extra bits, right? There must be a system.
Oh, definitely not random. Redundancy is achieved through various coding schemes. These are specific mathematical algorithms.
Yeah.
The sender uses a scheme to create a defined relationship between the original data bits and the redundant bits it adds. The receiver knows the same scheme, the same relationship.
So it checks if the relationship still holds true.
Precisely. If the relationship is intact when the message arrives, the receiver assumes, okay, no error detected. If the relationship is broken, it knows an error must have occurred. And these coding schemes fall broadly into two major categories: block coding and something called convolution coding. We'll focus mostly on block coding.
Okay, let's dig into block coding then. How does that work in practice?
Right, so with block coding, we take our original message and chop it up into fixed-size chunks. These are called data words, and let's say each has k bits.
K bits of actual data.
Yep. Then, for each k-bit data word, we use our coding scheme to calculate and add our redundant bits. This creates a larger block called a code word, which has a total of n bits, where n is simply k plus r.
Okay, data plus redundancy equals code word.
Exactly. Let's take a super simple example, maybe k2, so 2 data bits, and we add r1 redundant bit, making n 3-bit code words.
Okay.
Let's say our scheme dictates that the data word 01 becomes the code word 011. If the receiver gets 011, it checks its list of valid code words, sees 011 is valid, and knows the original data must have been 01.
Simple enough. But what if an error flips a bit? Say 011 arrives as, 111.
Good question. Now, if 111 is not on the list of valid code words for our specific scheme, the receiver immediately knows, an error happened. It can detect the error.
But it can't fix it with just detection.
Not usually in this simple case, no. It would likely just discard the frame 111 and maybe rely on an ARQ mechanism to get it resent.
Okay, but what if the error is unlucky? What if 011 gets hit by, say, 2 errors and becomes 00, and 00 is a valid code word for a different data word, maybe 00?
Now you've hit the crucial limitation. If the error transforms one valid code word into another valid code word, the error becomes undetectable by that scheme. The receiver gets 0000, thinks it's perfectly fine, and wrongly extracts the data as 00.
Ouch. So the strength of the code really depends on how different the valid code words are from each other.
Exactly, you've nailed it. That's the core idea, which leads us directly to a fundamental way to measure this difference. Hamming distance.
Hamming distance. Sounds important. What is it?
The Hamming distance between two binary words of the same length is simply the number of bit positions in which they differ.
Okay, how many places you need to flip bits to turn one into the other?
Spot on. So the Hamming distance between 000 and 011 is 2, because they differ in the second and third positions.
Got it. And Baven 101 and 1111 10. Let's see, first is same, second differs, third same, fourth differs, fifth differs. So distance is 3.
Perfect. Now, the really critical measure for a coding scheme isn't just the distance between any two words, but the minimum Hamming distance, usually written as daemon.
Daemon. No?
Daemon is the smallest Hamming distance between any possible pair of valid code words in the entire scheme. This single number, daemon, tells us a huge amount about the code's power.
How so? What does it tell us?
It gives us guarantees. To guarantee the detection of up to S single-bit errors, the daemon of the code must be at least S plus 1.
Okay, so daemon India 3 detects up to 2 errors.
Correct. And for error correction, the bar is higher. To guarantee the correction of up to T single-bit errors, the daemon must be at least 2T plus 1.
2T plus 1. So for daemon T3, 2T plus 1 means T1. It can correct 1 error.
Precisely. A code with daemon equal 3 can detect up to 2 errors or correct a single error. This daemon value is like the spec sheet for the code's error handling capability.
That's a really powerful concept.
Yeah.
That daemon dictates everything. So let's look at some actual practical coding schemes. You mentioned parity checks.
Right. The simple parity check code is probably the most basic block code. You take your k bits of data and you add just one extra bit, the parity bit.
Just one bit.
Yep, and that bit is chosen very simply. It's set to either 0 or 1 so that the total number of ones in the resulting n equals k plus 1 bit code word is always, say, even. Or you could choose odd.
Okay, so if my data is 1011, that has 3 ones. For even parity, I'd add a 1 to make it 100111, now 4 ones.
Exactly. Now, what's the daemon for this code? Think about flipping one bit. It changes the parity from even to odd or vice versa. So a single error is always detectable.
Right.
But flip 2 bits and the parity flips back. So 2 errors might cancel out. The minimum distance to get from one valid even parity code word to another valid even parity code word is 2. So daemon equals 2.
And what does dmend2 guarantee again? S plus 1 equals 2 means S was 1. Detects one error, 2t plus 1 equals 2. Doesn't really work for t.
Correct. It's a single-bit error detecting code. It can reliably detect any odd number of errors, 1, 3, 5. But it cannot detect an even number of errors, and it cannot correct any errors at all.
A classic blind spot. So useful but limited. For more power, we need codes with higher daemon, like Hamming codes.
Exactly. Hamming codes are cleverly constructed specifically to achieve a daemon of 3.
Okay, and daemon 3 means detect up to S2 errors, correct up to T1 error. Much better.
Much better. They represent a significant step up in capability. Then you get into even more sophisticated families like cyclic codes.
Cyclic?
Yeah, they have this neat mathematical property where if you take a valid code word and rotate its bits cyclically, you get another valid code word. A very important subset of these is used for cyclic redundancy check, or CRC.
Ah, CRC. I've definitely seen that acronym.
You bet. CRC is incredibly widely used, especially for error detection in networks like Ethernet and Wi-Fi. It uses a polynomial division in the background to generate a really robust check sequence. It's very good at catching common burst errors.
Okay, so polynomial math makes for strong error detection. What about the internet checksum? Is that related?
It's another method, yeah, but generally simpler than CRC. Traditionally, the internet protocols like IP and TCP have used a 16-bit checksum.
How does that one work?
Basically, the sender treats the data as a sequence of, say, 16-bit numbers, adds them all up using one's complement arithmetic, and then takes the one's complement of the final sum. That result is the checksum.
Okay.
The receiver does the same addition on the data it receives and adds in the checksum it received. If the final result is all ones in one's complement, it assumes no error occurred.
Simpler, maybe faster, but maybe not as robust as CRC.
Generally, that's the trade-off, yes. It's computationally cheaper, but might miss certain types of errors that CRC would catch.
Okay, so we've got our data protected by these clever coding schemes. But just getting the bits right isn't the whole story, is it? We need to organize them and manage how they flow onto the network cable or through the air. This sounds like the job of the data link layer you mentioned earlier.
Exactly. The data link layer, sitting between the physical layer, dealing with raw bits and signals, and the network layer, handling routing across networks, has these crucial responsibilities.
It's often helpful to think of it as having 2 sublayers.
2 parts, okay.
Yeah, conceptually. There's the logical link control, LLC, sublayer on top, which often handles things like identifying the network layer protocol and some flow and error checking logic we've touched on.
And below that?
Below that is the media access control, MAC, sublayer. This is the real traffic cop. Its primary job is figuring out how to get data packets or frames from one network interface to another across a shared channel. Think multiple computers plugged into the same Ethernet hub or lots of devices on the same Wi-Fi network. Got it. LLC is more logical connection stuff. MSC is about accessing the physical wire or airwaves. Before we get to the traffic cop part, though, you mentioned frames. How do we package these bits up? That sounds like framing.
Spot on. Framing is all about taking that stream of bits coming down from the layers above and organizing it into discrete units called frames. It's like putting letters into envelopes so the Postal Service knows where one piece of mail ends and the next begins.
Makes sense. How do you mark the start and end?
Well, sometimes it's simple. Fixed size framing. If every frame is exactly, say, 1,000 bits long, the size itself acts as the delimiter. But that's not very flexible.
Right, data isn't always the same size.
Exactly. So more common is variable size framing. Here you need explicit markers, special delimiters, to signal the start and end of each frame. The big challenge then becomes, what if those special delimiter patterns accidentally appear inside your actual data?
Yeah. The receiver might think the frame ended early or started late. That would mess things up badly.
Totally. So we need ways to handle that. One approach is character-oriented framing, often used when data is seen as 8-bit characters or bytes. You use a special flag byte, like maybe the ASCII data link escape, to mark frame boundaries.
But what if DLE is part of the actual data?
Then we use byte stuffing. If the sender encounters a DLE byte within the data it needs to send, it just inserts or stuffs an extra DLE byte right before it.
Okay.
The receiver knows this rule. If it sees 2 DLE bytes in a row, it knows the second one was the actual data, and it just removes or unstuffs the first one. A single DLE followed by something else still means a control function, like end of frame.
Clever. So you use escaping to differentiate data from control. What about if you're not thinking in bytes, but just bits?
Then we use bit-oriented framing. Here, a special bit pattern, often 01111011 now, a 0, 6 ones, and a 0, is used as the flag delimiter at both the start and end of the frame.
Okay, but same problem, right? What if my data happens to contain 01111011 now?
Same problem, similar solution. Bit stuffing. The rule is typically, if the sender sees 5 consecutive 1 bits in the data stream, it automatically inserts an extra 0 bit right after the 5th one.
Regardless of what the next bit would have been.
Yes. This guarantees that the pattern 01111110 can only appear as a real flag, never accidentally within the data. The receiver knows this rule too. If it sees 5 consecutive 1s followed by a 0, it automatically plucks out that 0s, restoring the original data. If it sees 5 1s followed by a 1, it checks the next bit. If that's a 0, it's a flag. 01111111.
Wow. That's subtle but really effective. The core idea is this stuffing, adding temporary bits or bytes to avoid ambiguity.
Exactly. It ensures frames are always clearly separated.
Okay, frames are defined. Now, back inside the data link layer, you mentioned flow control and error control again. How does it differ here compared to, say, the transport layer?
Good question. There's overlap in concepts, but the scope is different. Flow control here is specifically about the link between 2 adjacent nodes, making sure a potentially fast sender doesn't swamp the buffer or processing capacity of the immediate next hop receiver.
Okay, neighbor-to-neighbor speed matching.
Right. And error control at this layer, while using the detection schemes we discussed, like CRC, primarily relies on automatic repeat request, ARQ, for correction. If a frame arrives corrupted, CRC fails, or doesn't arrive at all, the data link protocol will arrange to retransmit it over that specific link.
So ARQ is key here. Let's look at some protocols that use it. Maybe start simple, even if just theoretical. What about a perfect noiseless channel?
Well, in theory, on a perfectly noiseless, infinitely fast receiver channel, you wouldn't need flow or error control. You could just blast frames out. But that's not reality.
Right.
A slightly more realistic but still basic protocol for flow control is stop and wait. The sender sends exactly 1 frame, then stops and waits for an acknowledgement, an ACK, from the receiver saying, got it, ready for the next one.
Okay, send one, wait for, okay, send the next. Sounds slow.
It is incredibly slow, especially on modern networks. Like you said earlier, waiting for a reply to one text before sending the next.
Yeah, and what happens when you add noise? So now we need stop and wait ARQ.
Now it gets even more interesting, and the inefficiency becomes clearer. The sender sends frame 0, starts a timer, and keeps a copy. If the ACK for frame 0 comes back before the timer expires, great, send frame 1.
But if the frame gets lost, or the ACK gets lost,
Then the timer expires. The sender doesn't know what got lost, only that it didn't get the confirmation, so its only safe option is to resend frame 0.
okay, so it handles errors, but that waiting period seems like a killer.
It is, especially on links that have high bandwidth, they're thick pipes, and/or high round-trip delay, they're long pipes.
Right.
Think satellite links, for example.
Right.
There's a concept called the bandwidth delay product. It basically calculates how many bits could physically be in flight on the link during one round-trip time.
Like the volume of the pipe.
Exactly. If your frames are much smaller than this bandwidth delay product, stop and wait means the pipe is mostly empty. You send a small frame, then wait, while potentially megabits of capacity go unused. Utilization can be terrible, like 5% or even less sometimes.
Okay, that's clearly not going to work for demanding applications. How do we fill that pipe? How do we improve efficiency?
The key is pipelining. Instead of stop and wait, we allow the sender to transmit multiple frames before needing to wait for an acknowledgement for the first one, get several frames in the pipe simultaneously.
Keeping the data flowing. Makes sense. What protocols use pipelining?
The 2 big ones implementing ARQ with pipelining are go back N ARQ and selective repeat ARQ.
Okay, let's take go back N first. How does that work?
With Go Back N, the sender can send up to N frames without waiting for ACKs. It keeps copies of all these unacknowledged frames just in case. Frames are numbered sequentially, usually modulo some power of 2.
And the receiver.
The receiver expects frames to arrive in perfect order. If frame 5 arrives correctly, it sends an ACK saying, "I'm ready for frame 6." Now here's the catch. Suppose frame 5 is sent, then frame 6, then frame 7, but frame 6 gets corrupted.
Right.
The receiver gets frame 5 fine, then it gets the corrupted frame 6, discards it, then frame 7 arrives, but frame 7 is out of order. The receiver also discards frame 7 and any other subsequent frames, even if they're perfectly fine.
Whoa, really? It throws away good frames just because one was bad earlier.
Yes, it only accepts frames in perfect sequence. When the sender's timer for frame 6 eventually expires, because it never got the ACK for frame 6, it has to go back N, meaning it resends frame 6 and frame 7 and everything else it had sent after frame 6.
Oof. That sounds potentially wasteful, especially if the link is quite noisy and errors happen often. You could be resending a lot of perfectly good data.
Exactly. That's the main inefficiency of Go Back N, particularly on unreliable links, which leads us naturally to the more refined approach.
Which must be selective repeat ARQ. How does that improve things?
Selective repeat addresses that exact inefficiency. If a frame is damaged or lost, only that specific frame is resent.
Much smarter.
Much more efficient in terms of bandwidth, yes. The receiver, in this case, does accept and buffer out-of-order frames that arrive correctly. So if frame 6 is lost, but frame 7 arrives fine, the receiver holds on to frame 7. When frame 6 is eventually retransmitted and arrives okay, the receiver can then pass frame 6, frame 7, and so on up to the next layer in the correct order.
That makes way more sense. What's the catch? It sounds better in every way.
The catch is complexity, primarily for the receiver. It needs more sophisticated logic and buffer management to handle those out-of-order arrivals and reassemble the stream correctly. Go Back N is simpler to implement, so it's a classic engineering trade-off. Network efficiency versus implementation complexity.
Got it. And you also briefly mentioned piggybacking earlier.
Oh, right. Yeah, piggybacking is just a small optimization. If a station has data to send and an acknowledgement to send back for data it just received, it can sometimes combine them into a single frame. Saves a bit of overhead by not sending a purely ACK frame.
Neat little trick. Before we move off protocols, we should probably mention HTLC. Sounds like an important standard.
Yes. High-level data link control, HDLC, is a classic, quite influential bit-oriented protocol. It was developed by ISO and serves as a basis for many other data link protocols. It's a concrete example that implements many of these ARQ concepts we've discussed.
What does it do specifically?
It provides mechanisms for reliable data transfer over point-to-point and even multi-point links. It defines specific frame structures with fields for flags, using that 0, 1, 1, 1, 1, and 110 pattern with bit stuffing, addresses control information, which indicates frame type, sequence numbers, etc., the actual information payload, and a frame check sequence, usually CRC, for error detection.
Does it have different ways of operating?
Yeah, it defines several modes. For example, normal response mode, NRM, is for unbalanced configurations, like one primary station controlling multiple secondary stations. The secondaries only speak when spoken to by the primary. Then there's asynchronous balanced mode, ABM, common in point-to-point links, where both stations are peers and either can initiate transmission.
Okay, so we've covered organizing data, framing, handling errors, detection correction, RQ, and managing flow, stop and wait, pipelining. But we skirted around a huge issue you mentioned earlier with the MI sublayer. What happens when multiple stations want to use the exact same physical channel at the same time, like everyone on the office Wi-Fi?
Right, this is the multiple access problem, and it's absolutely central to how LANs and wireless networks function. If you have a shared medium, a single cable, a shared radio frequency band, you absolutely need rules to coordinate who gets to transmit when, to avoid collisions, and ensure some level of fairness. This is the core job of that media access control, MAC sublayer.
Okay, traffic control time. What are the main strategies? Like you mentioned a Wild West approach first.
Yeah, that's a good way to think about random access protocols, sometimes called contention-based protocols. The basic idea is send if you dare.
No coordination.
Essentially, no station is assigned control, and there's no predefined schedule. Each station decides independently, based on the protocol rules, whether or not to try sending. The big, obvious problem: stations might decide to send at the same time.
Collision.
Exactly. If two frames overlap in time on the shared medium, even slightly, they interfere with each other, and typically both become garbled and useless. The data is lost.
So how did the earliest systems handle this? You mentioned Aloha.
Yes, the Aloha network, developed at the University of Hawaii, was one of the very first random access systems initially for radio communication. In its simplest form, pure Aloha, the rule was dead simple. If a station has a frame to send, it just sends it immediately.
That sounds like guaranteed chaos.
It was pretty chaotic, yeah. If a collision occurred, which was likely, the sender would eventually figure it out because it wouldn't receive an acknowledgement from the destination. Then it would wait a random amount of time and try sending again.
Why random?
Crucial point. If both colliding stations waited the same amount of time, they'd just collide again. The randomness helps them stagger their retransmissions.
Okay, but still, collisions must have been frequent. How efficient was it?
Not very. The maximum achievable channel utilization, or throughput, for pure Aloha is only about 18.4%. That means over 80% of the channel's capacity is wasted due to collisions or sitting idle.
Yikes. Not great. Was there an improvement?
Yes, a significant one came with slotted Aloha. The idea here was to divide time into discrete intervals, or slots, exactly equal to the time it takes to transmit one frame. Stations were then only allowed to start transmitting at the beginning of a time slot.
How does that help?
It drastically reduces the window of vulnerability. In pure Aloha, frames could overlap partially. In slotted Aloha, frames either miss each other completely or they overlap entirely within a slot. This simple change doubled the maximum throughput to about 36.8%. Still not amazing, but much better.
Okay, so coordinating timing helps, but Aloha is still basically transmit and pray. What came next? A bit more intelligence.
Exactly. The next major step was Carrier Sense Multiple Access, or CSMA. The key idea here is often summarized as listen before talk.
Check if anyone else is already using the channel.
Precisely. Before attempting to transmit, a station using CSMA first senses the medium, listens for a carrier signal to check if it's currently busy. If it senses an idle channel, it transmits. If it senses a busy channel, it waits.
That sounds much more polite. Does it eliminate collisions entirely?
Unfortunately, no. It reduces them significantly, but it doesn't eliminate them. Why? Because of propagation delay.
The time it takes the signal to travel.
Right. Imagine two stations at opposite ends of a long cable. Station A listens, hears silence, and starts sending. But its signal takes time to travel down the cable. Just before A's signal reaches Station B also listens, hears silence because A's signal isn't there yet, and also starts sending.
Boom! Collision again, even though they both listened first.
Exactly. The vulnerable period is now much shorter. It's basically related to that propagation time, but it still exists.
Okay, so CSMA is better, but not perfect. How did we get to the kind of reliability we expect from wired Ethernet today?
That required another crucial refinement. CSMA with collision detection, or CSMA. This is the bedrock of traditional Ethernet. The tagline here is, listen before and while talking.
Listen while talking. How does that work?
It enhances CSMA by having the station continue to monitor the transmission medium even as it is sending its own frame.
Okay. What does that achieve?
If, while sending, the station detects that the signal on the medium is different from what it's trying to transmit, for example, it detects a higher energy level, it immediately knows a collision has occurred.
It catches the collision in progress. What does it do then?
It immediately stops transmitting its data frame. Then it sends out a brief jamming signal to make absolutely sure all other stations involved in the collision also detect it. After the jamming signal, it waits a random amount of time using an algorithm called exponential backoff, and then tries the whole process again: listen, transmit while listening, etc.
That sounds really robust. Is there a catch or a requirement for it to work?
Yes, there's a absolutely critical timing constraint. For CSMD to function correctly, the time it takes to transmit the smallest possible frame, TFR, must be at least twice the maximum propagation delay, TP, across the network segment. TFR equal 2 TP.
Twice the propagation delay. Why that specific relationship?
Think about the worst-case scenario. Station A starts sending, and just before its signal reaches the farthest station B, B also starts sending, causing a collision. A needs to still be transmitting when the evidence of that collision, the garbled signal, propagates back to A. If A finished sending its frame before the collision signal got back, it would wrongly assume the transmission was successful.
So the frame has to be long enough to keep talking until the news of the collision could possibly return.
Exactly. And this fundamental requirement, TFR equals 2 TP, directly leads to the concept of a minimum frame size in Ethernet. Anything smaller, and collision detection wouldn't be guaranteed.
That's a huge aha moment. The minimum Ethernet frame size isn't just arbitrary padding. It's required for CSM data function.
You got it. It's a direct consequence of the physics and the protocol design.
Okay, CSMND is great for wires where you can easily listen while talking. But what about wireless? Like Wi-Fi? You can't really detect a collision accurately while your own radio is blasting out a signal, can you?
That's a major challenge for wireless, yes. It's much harder, often impossible, for a standard radio to effectively detect collisions while transmitting. So wireless LANs like Wi-Fi use a different approach. CSMA with collision avoidance, or CSMATA. The goal shifts from detecting collisions to avoiding them as much as possible in the first place.
Avoidance, not detection. How do they try to achieve that?
It uses several strategies. First, even if a station senses the channel is idle, it waits for a short, fixed period called an interframe space, IFS, before potentially transmitting. Different IFS lengths can be used to prioritize different types of traffic.
Okay, a little pause for politeness.
Kind of. Then, it typically enters a contention window. It picks a random number of time slots within this window and waits for that duration before sending. If the channel becomes busy during its countdown, it freezes the timer and waits until it's idle again before resuming the countdown. The randomness here helps prevent stations that become ready at the same time from all transmitting simultaneously.
So, randomized weighing to hopefully avoid stepping on toes. But collisions can still happen, right? How does it know if the frame got through?
Since it can't reliably detect collisions, CSMAC relies heavily on positive acknowledgments, ACKs, from the receiver. If the sender doesn't receive an ACK within a certain time, it assumes a collision or other error occurred and will retransmit the frame, often using a backoff mechanism similar to CSMAC where the contention window size increases after failures.
So it infers collisions from missing ACKs. Does CSMAC help with other wireless issues, like that hidden terminal problem?
It can help mitigate it, yes. The hidden terminal problem is where Station A can talk to the access point AP and Station C can talk to the AP, but A and C can't hear each other. They might both transmit to the AP at the same time, causing a collision at the AP that neither sender detects directly.
Right.
Mechanisms often used with CSMAC, like request to send, clear to send, RTS, CTS, can help. A station sends an RTS to the AP. The AP broadcasts a CTS, which includes how long the transmission will last. Even hidden stations hear the CTS and know to remain quiet for that duration, thus avoiding the collision.
Okay, so Aloha, CSMA, CSMSD, CSMAC, those are all random access or contention methods. Stations kind of compete. Are there other ways, more cooperative methods?
Yes, those fall under the umbrella of controlled access methods. Here, stations don't just transmit whenever they think the channel might be free. They coordinate, usually by consulting each other or a central controller, to determine which station has the right to send at any given time. Collisions, in theory, shouldn't happen if the protocol works correctly.
How do they coordinate?
There are a few main approaches. One is reservation. Time is divided into intervals. Each interval might start with a mini frame containing reservation slots. Stations wanting to send data in the main part of the interval first have to reserve a slot during that initial reservation period.
Like booking a time slot in advance.
Exactly. Another method is polling. This is common in systems with the primary-secondary relationship. One device is designated the primary station, like a master, and the others are secondary stations, slaves. All communication typically goes through the primary.
So the primary controls everything.
Pretty much. The primary can use a select function if it wants to send data to a specific secondary, or it can use a poll function to ask a specific secondary, do you have anything to send me? The secondary only transmits if it's polled and has data.
Very centralized control. What else?
A third major controlled access method is token passing. This is often used in ring topologies, either physical or logical. Stations are arranged in an order, and a special small frame called the token circulates around the ring.
The token, what does it do?
Only the station that currently holds the token is granted permission to transmit its data frame. After it's done sending, or after a set time limit, it passes the token along to the next station in the logical ring. If a station gets the token but has nothing to send, it just passes it immediately.
So possession of the token grants transmission rights. Seems fair, but you need to manage that token carefully, right? What if it gets lost?
Absolutely. Token passing schemes need mechanisms to detect a lost token. For instance, if it doesn't reappear after a maximum expected time and regenerate it. They also need ways to handle stations joining or leaving the ring, and potentially ways to assign priorities so some stations might get to hold the token longer or more often.
Okay, so random access competition versus controlled access cooperation.
Yeah.
Is there a third category?
Yes, there's also channelization, which is a bit different. It's less about when you can talk and more about dividing the shared channel itself into smaller dedicated subchannels, so
Yeah.
multiple users can transmit simultaneously without interfering. It's conceptually similar to multiplexing at the physical layer.
Dividing the bandwidth. How's that done?
Three main ways. Frequency division multiple access, FDMA, gives different users distinct frequency bands within the overall channel bandwidth. Think different radio stations using different frequencies.
Okay.
Time division multiple access, TDMA, assigns fixed, repeating time slots to different users on the same frequency. Your phone might get slot 1, mine gets slot 2, someone else gets slot 3, then it repeats.
Got it. Frequency slices or time slices? What's the third?
The third is code division multiple access, CDMA, which is quite clever. In CDMA, all users transmit in the same frequency band at the same time.
How on earth does that work without interference?
They are separated by unique codes. Each station is assigned a unique spreading code, also called a chip sequence. These codes are designed to be orthogonal, meaning they don't interfere with each other mathematically.
Orthogonal codes. Like they cancel each other out unless you have the right key.
Sort of. The receiver knows the specific code of the sender it wants to listen to. It uses this code to decode the desired signal, while all other signals, using different codes, just look like low-level background noise and are effectively filtered out.
Wow. So everyone talks at once, but you only hear the person speaking your language or using your code.
That's a great way to put it. These chip sequences often come from structures like Walsh tables, which guarantee the orthogonality needed.
Okay, that's a lot of ways to manage access. Let's try to tie some of this together now by looking at the absolute workhorse of wired networking, standard Ethernet, technically known as IE 802.3. Where did this standard come from?
Right, so the IE 802 project was started back in 1985 by the IE Computer Society. Its goal was huge, to create standards that would allow networking equipment from different manufacturers to actually talk to each other, a massive boost for interoperability.
And Ethernet was one of the key things they standardized.
Exactly. The 802 project focuses on standards for the physical layer and the data link layer, specifically that ME sublayer we discussed, for major LAN protocols. Ethernet itself, though, originated a bit earlier, famously at Xerox's Palo Alto Research Center, Eric, around 1976. It's gone through many generations since then, getting faster and faster. The IE 802.3 standard codifies it.
So let's look under the hood. What does that standard 802.3 ME say-ware frame actually look like? What are the pieces?
Okay, an Ethernet frame starts with a preamble. It's 7 bytes of alternating ones and zeros, 10101010 repeated. This basically gives the receiver's hardware a chance to lock on to the incoming bit timing.
Like a little wake-up and synchronize signal.
Precisely. Immediately following the preamble is the start frame delimiter, SFD. It's just 1 byte, 101011. That last 11 breaks the alternating pattern and tells the receiver, okay, sync is done, the actual frame starts now, and the destination address is next.
Got it. Preamble for sync, SFD for here comes the frame, then the addresses.
Yep. First comes the destination MSE address, which is 6 bytes long. This specifies who the frame is intended for. Then comes the source image address, also 6 bytes, identifying the sender.
These MSC addresses, the
Yeah.
new hardware addresses, right? How do you know if it's for one device or a group?
Good question. There's a specific bit within the first byte of the destination MSC address, the least significant bit, actually, that indicates the type. If that bit is 0, it's a unicast address, meaning it's intended for a single specific network interface card.
Okay, and if it's 1?
If it's 1, it's a multicast address intended for a group of devices. There's also a special multicast address, the broadcast address, which is all ones, hex, FF. That means the frame is intended for every device on that local network segment.
So unicast for one, multicast for some, broadcast for all, based on 1 bit in the destination address. Clever. What comes after the source address?
Next is a 2-byte field that has a dual purpose. It can be either a length field or a type field.
Length or type? How does it know which one it is?
There's a threshold value. If the value in these 2 bytes is less than or equal to 1500 decimal, it's interpreted as the length of the data payload that follows. If the value is greater than 1536, it's interpreted as a type field, indicating which network layer protocol, like IPv4, IPv6, ARP, is encapsulated within the frame's data section. Values between 1501 and 1535 are undefined.
Okay, so it tells you either how long the data is or what kind of data it is. Then comes the actual data.
Exactly. The data field, sometimes called the payload, This carries the actual information passed down from the upper layers. Now, remember that CSMCD minimum frame size requirement?
Yeah, TFR is 2TP.
Right. Because of that, the data field must contain at least 46 bytes. If the actual data from the upper layer is less than 46 bytes, the sending station has to add padding, usually zeros, to bring it up to the minimum.
Ah, so the padding ensures the total frame meets the minimum length for collision detection.
You got it. There's also a maximum size for the data field, typically 1,500 bytes in standard Ethernet. If the upper layer tries to send more than that in one go, it needs to be fragmented into multiple frames.
So data is 46 to 1,500 bytes. What's the very last part of the
The
frame?
last part is the frame check sequence, FCS. This is typically a 4-byte, 32-bit CRC value.
Ah, the error detection we talked about.
Exactly. The sender calculates the CRC based on the contents of the destination address, source address, length type, and data fields. It puts that calculated CRC in the FCS field. The receiver performs the exact same calculation on the fields it receives.
And if the receiver's calculated CRC matches the CRC value in the FCS field.
It assumes the frame arrived without errors. If
Huh.
they don't match, the receiver knows the frame was corrupted during transmission and simply discards it. It relies on upper layers or ARQ mechanisms to handle the retransmission.
So putting it all together, preamble, SFD, dest en masse, source en masse, length type, data, padded if needed, and CRC. That's the Ethernet frame.
That's the standard structure, yes.
What's the total size range that, excluding the preamble, which is more physical layer sync?
Right, excluding the preamble and SFD. The minimum frame size is dictated by the minimum data, 46 bytes, plus the addresses,
Yeah.
6 plus 6, 12 bytes, length type, 2 bytes, and CRC, 4 bytes. That's 46 plus 12 plus 2 plus 4 equals 64 bytes.
64 bytes minimum.
Max
Maximum data is 1,500 bytes. So 1,500 plus 12 plus 2 plus 4 equals 1,518 bytes maximum.
64 to 15, 18 bytes. A very well-defined structure.
Yeah.
One last detail. How are those MEC addresses actually sent over the wire? Is it just byte by byte? Mostly, yes, byte by byte, left to right as we'd normally write them. But there's a twist. Within each byte, the bits are typically transmitted least significant bit, LSB, first.
LSB first. So if a byte is, say, hex 47, which is binary 010111, it goes out as 11100017.
Exactly like that. The bits within each byte get reversed for transmission on standard Ethernet. It's just one of those historical details you have to know.
Good to know. So we've covered the basics of standard Ethernet. Of course, it's evolved massively since then, right? Gigabit, 10 gigabit Ethernet.
Oh, absolutely. The fundamental MSC frame structure has remained remarkably consistent, but the physical layers and speeds have advanced incredibly. But the core principles of framing, addressing, error detection, and that CSMCD heritage, though often less relevant in modern switched networks, are still foundational.
Wow. Okay, we have really navigated the intricate world of the data link layer today. We started with that basic problem of data getting corrupted.
Right, the bit flicks.
Yeah, and looked at the ingenious solutions like redundancy, Hamming distance, block coding, CRC.
The whole toolkit for error detection and correction.
Then we explored the rules of the road for sharing a channel, that whole maxi sublayer stuff. From the Wild West of Aloha
To the more polite listen before talk of CSMA.
and the really clever listen while talk of CSMAD-DT for Ethernet, and the collision avoidance strategies in CSMACI for Wi-Fi.
And the controlled access methods, too, like token passing.
Right. And finally, we peeked under the hood of Ethernet itself, seeing how all those pieces fit together in the 802.3 frame.
It really is amazing when you pause to consider it. Every email, every web page loading, every video call, every streamed movie you enjoy, it absolutely relies on these precise, often totally invisible mechanisms working constantly.
Yeah.
These aren't just abstract textbook concepts, you know? They are truly the bedrock of our connected world, all designed specifically to overcome the inherent messiness and challenges of just sending bits across a wire or through the air.
They really are the unsung heroes of our digital existence. So, okay, for our provocative thought today, building on all this,
Think about this. Given the absolutely mind-boggling volume of data flowing across networks constantly, every second of every day, and given that there's always this tiny persistent probability of an error occurring on any transmission, just how much more chaotic, how much more unreliable and frustrating would our digital lives be if we didn't have these incredibly robust systems for error detection, correction, and access control working tirelessly behind the scenes?
it would be unusable probably.
Almost certainly, and maybe flip that around. What seemingly tiny change or tweak in one of these foundational protocols, framing, error coding, access method, could potentially have the most dramatic, maybe unexpected impact on our daily digital experiences.
That's definitely food for thought. What small lever could have the biggest effect? Interesting.
Something to ponder.
Indeed. Well, that's all the time we have for this episode. Join us next time on The Deep Dive.